All right, so this is going to be a video on the second semester final study guide for stats. Um, so let's go ahead and get to this. I'm going to skip the top part. I might do that at the end of this video, or maybe make a separate video for it, just because that's fill in the blank stuff. It's pretty standard fare. I want to focus on the one that are probably going to be causing most of your time, right? So let's get to it. So the first one here says, out of 2,000 students, 850 of them picking their toes. Test the claim that less than 44% of the students pick their toes. All right. So what we want to figure out here, just making sure my mic is working. Okay. What we want to figure out here is two things right off the bat. Are we testing for a percentage, an average, or a deviation? And is it a one sample or two sample situation? So what are we testing for and how many samples are there? So in this case, we're testing one single sample. This 2,000 students, that is our one sample. And we're comparing it to a benchmark of 44%. So we're comparing one sample to a number. So this is a one sample test. And we're testing it to a proportion. We're testing it to a percentage. So that means that we're going to have my initial and my alternative hypothesis be p's, because we're testing a percentage, equal to 0.44 is my first one, and then less than 0.44 is my second one. And this is actually my claim. That's the one I'm trying to get for, right? That's what I'm trying to do or figure out. And so if we're testing a single percentage, a single samples percentage, then we're going to use the one prop z. So test one prop z, because we have one sample and we're testing it against a single proportion or a single benchmark. And so we type in 0.44, 850, 2000. So again, this is the claim percentage. This is the number of successes. This is the number of samples, or number of students in this case, because it's how many samples we have. We want it to be less than 0.44. And we want to calculate. And these are my values. So my two numbers up here, my first two numbers that I really need. So my z number is my test stat. So my z number is negative 1.35. My p-value was 0.088. And since we're using a 0.05 significance, that is certainly bigger than 0.05. 0.88 or 0.088 is bigger than 0.05. And so since the p is high, that means it's not a rare event. So we're going to fail to reject HO. So we're going to fail to reject HO. So we're going to go with HO. HO is our guy. Well, unfortunately, my claim was not HO. So this would not support the claim, because, again, it's not rare enough to be significant, is another way of putting it. My mic is still on. So that's how we do that one. Again, ask yourself, what are you testing? Percentage, average, or variance? And then how many samples do you have? One or two? This one, a juggler is attempting to juggle some chainsaws. Out of 36 attempts, they were able to, on average, so we're testing an average here, juggle 6 chainsaws with a deviation of 2.05. Now, this is the sample deviation, because this is the deviation that he got. Not of all jugglers, but just him. That's a sample deviation. Test the claim that he can juggle more than 4 chainsaws. So we already said that we're testing an average, right? So my HO is going to be mu is equal to 4, because I'm claiming that he can juggle more than 4. And my H1 is going to be that mu is bigger than 4. And that's my claim. So we have a single sample average situation. We're comparing a single person's average to some benchmark. So to do that, we're going to go test, and it's either z or t. So which one do we have, z or t? Z or t? Well, since this deviation is to the sample, aka just to him, not to the entire population of jugglers, but just specifically to him, since it's a sample deviation, we're going to be doing a t-test, because sample deviation is less than ideal information, so we're using a t-test because it's more widespread. It has more cautious in its assertions, essentially. So once again, sample deviation, you go with a t-score test. We had 36 attempts. On average, he was able to get 6. Oh, sorry, my bad. 4 is our claimed average, so we're claiming that he can juggle 4 or more than 4. He was able to juggle 6 on average. His deviation was 0.205, and he made 36 attempts that we took data from. And we want to claim that we're more than 4. Again, your average that you're testing for, you want to be more than 4. So 4 is your mu 0. You want to be more than 4, so you pick the end one there. It's a common mistake. And so we get a t-score of 5.85. So my test stat, remember your test stat is just the score you get, Z, T, chi, F, those are all your test stats. So 5.85, and my p-value was 6.02 times 10 to the negative 7. That E there means times 10 to the negative 7, which means this is a very small number. Remember, your p-value cannot be more than 1. So if you see a 5 point or a 6 point or a 7 point or a 3 point something, that means there's an E to the negative something at the end. So this is a very, very, very small number, definitely smaller than 0.05. So my p-value is 6.0, what was it? 2. 6.02 times 10 to the negative 7th, and that is much smaller than 0.05. Remember, this means that you have basically 6 zeros in front of the 6. So you have 0.000000602, which is definitely smaller than 0.05. So this is a very rare event. So we're going to reject HO because my P is low. So if the P is low, you reject the null, reject HO, reject HO. And therefore, we're going to go with my claim because my claim was not HO, my claim was the other one. So we're going to support the claim. The next one sounds very similar, right? We have 56 cookies. The average number of chocolate chips in them was 12. The population deviation, this is key here, the population deviation of all cookies of this type is 2.85 chips. And we want to claim that the average number of chocolate chips in these cookies is 14. So again, we're testing a claim about an average again. We're testing an average again. So my mu is going to be the same. So HO is mu equals 14. H1, in this case, since I'm claiming that they're equal, my alternative is simply that they're not equal. Not more, not less, but simply not equal to. If you're claiming equality, then the opposite is inequality, or not equal to. And so now you're going to run your test, but again, ask yourself, what kind of test? 1 or 2 sample? Well, again, I'm testing a single brand of chocolate chip cookies to a benchmark. So this is a single sample average test, which means it's going to be either a Z or a T. Well, in this case, since we have the population deviation, it's going to be a z-score test. Okay? And we enter our data in the same way. 12, deviation of 2.85. Average we got was, sorry, my bad. This is supposed to be 14. 14 is our claimed average. The average we got was 12, and we had 56 cookies that we tested, and where alternative is not equal to, boom, z-score is negative 5.25. So z-score is negative 5.25. And my p-value is 1.51 times 10 to the negative 7. And once again, that is a very small number, definitely smaller than 0.05. So we're going to reject HO, which means in this case we are not going to support the claim because, again, I'm rejecting my claim because my claim was HO. So we do not support. So again, this is the question I often get asked is, well, you rejected, therefore that means what? Well, rejecting or not rejecting does not indicate whether you support or not support. What indicates whether you support or not support was whether you rejected or did not reject your claim. So in this case, we rejected HO, but that was good because my claim wasn't HO, my claim was the other one. In this case, we rejected HO, but that was bad because my claim was HO. So this part right here, to support or not support, that depends not only on what you reject, but what your claim was. That's why I always tell people to put a little C next to whichever one they believe is their claim, because that will help them determine what this part is, right? So the next one here, we have the time it takes students' brain to implode. We want to claim that the deviation of these numbers here is more than 3. So we're testing a claim about a deviation, and it's from a single sample. So a single sample deviation test is a chi-squared test. Chi-squared is single sample deviation. Now, in order to do this, we need to find the standard deviation of these numbers. So we're going to enter them into our list. So 30, 28, 25, 32, 24, 31, 22, 28, 29. Good. All right, so then to find out the standard deviation of that list, we're going to go to second, calculate, 1 vars. And we get a standard deviation of 3.35. Remember, we're using SX here. So 3.35, which I believe is different than what I put on the study guide in print. So I might have made a mistake in print on the study guide one here. I'm sure you guys will figure that out and let me know if I did. But I think I did 9.3 rather than 3.35 for some reason. So in that case, my chi-squared form, this is a formula I will give you on the quiz, but you cannot do this one in the calculator. You have to do this one by hand. So the way you do it by hand is you first use the formula, which is n minus 1 times s squared over sigma squared. And so n is the number of samples you have, in this case 9 minus 1. S squared is your standard deviation that you get from your sample, which is 3.35 squared. And sigma squared is your claimed deviation, which is 3. All right. Also, I should probably write down my hypotheses. So HO is that sigma is equal to 3 because it's a deviation. H1 is that sigma is more than 3, and this is my claim. Okay, that's the claim. So you type this in, and you end up getting, let's see here, 9 minus 1 is 8 times 3.35 squared divided by 3 squared, which is 9. We get 9.98. 9.98 if I'm rounding. Now, the question then becomes, well, what about your p-value? If you're doing it by hand, you don't want a p-value because getting a p-value from this situation is kind of tricky. Instead, what you want is a critical value. This is kind of the other way of doing these here. Before they had calculators, they did it with the critical value way. So what's the critical value? Well, the critical value is when you take your alpha, which is 0.05, and you convert it into a chi-squared score in this case. You convert it into a score that you can compare it to the other one. So this is where it gets a little tricky here. My alpha is 0.05, right? That is my uncertainty level, we should say. And in this case, my claim is that sigma is more than 3. So my claim is a right tail claim, right? RT tail. This is a right tail claim. Well, luckily, my chi-squared table goes from the right. So if my tail test and my tail of the table agree, then I don't have to do anything. Then I can just look up 0.05 on my table and I'm good with it, right? But if they disagreed, then I would have to do the 1 minus thing, where I do 1 minus 0.05 and look up 0.95 instead. But in this case here, I don't have to bother with that because the tail of my table and the tail of my test are both right. They agree. We're all good. Okay. So in this case here, I'm going to look under the 0.05 column, and I'm going to have 8 degrees of freedom because I have 9 samples. So 8 degrees of freedom, 0.05, we end up with 15.507. So over here, so this is going to lead us to be 15.507. So again, 0.05 on top, 8 degrees of freedom, find out where they cross, boom, there's my critical value. If I was going from the left, if I was testing to see if sigma was less than 0.03, I would do 1 minus 0.05, which gives me 0.95, and I'd look under this column, 0.95, 8, find out where they cross, boom, use that critical value. Okay? But that was if it was a left tail, because again, if it's a left tail, they disagree, and therefore I do the 1 minus trick. But in this case, I don't have to, so I just go with the flow. Now, how do you compare these? How do you get your reject, failed to reject, support, not support? Well, I would draw a graph. Right? Chi-squares are usually this sort of hump and down shape. I would graph your critical value first. So 15.507, that's like right here. 15.507. Okay? And we're going to shade to the right because it's a right tail test. Then you find out where 9.98 is. Well, 9.98 would be to the left of this, right? It'd be closer to 0. Right here's 0. So 9.98 would be something like, right here. 9.98. Well, if it's in this region, that is the fail to reject region. So in this case, we would fail to reject HO, and in that case, we would not support my claim. Because if we fail to reject HO, that means we're going to box it in. Oh, my claim is outside my box. My claim is not supported. Therefore, it's not supported. My claim is not part of the one that I'm going to take. That's not part of my my answer here, essentially. I believe, like I said, I got this one wrong on the study guide because I misdid my standard deviation as 9.3 rather than 3.35. Either that or I messed up on this one. So you can look at that one and let me know what you guys think. But I believe I messed up on the study guide now that I'm looking at this here on this one in particular. So it is a good thing I'm doing a video here. So that's how you do this one. Again, this is one of the ones that you have to do by hand. If you're doing a variance one or a standard deviation test, then you're going to have to do it by hand. You cannot do this one on the calculator, unfortunately. All right, number 13. It was found that 1,020 households, 950 of them had at least one pet. In Illinois, 980, 910 had at least one pet. Test the claim that the households in Michigan have at least one pet is more than the households in Illinois. So this is a 2-sample one, right? Because we have 2 samples. We have a sample from Michigan and a sample from Illinois, and we're comparing them. If we're comparing 2 samples, it is a 2-sample test. So In this case, I'm testing a percentage, right? So my H0 is going to be that. I'm going to put Michigan as my P1 here, right? So I'll put PM. So PM for Michigan is bigger than PI for Illinois. Oops, sorry, I'm doing my null. So this should be equals first. So I always start with equals. So equals, and then H1 is that PM for Michigan is more than PI for Illinois, because it says in Michigan that have at least one pet is more than that in Illinois. So again, think of this as P1, P2, P1, P2. I'm just putting PM and PI so we know which one is which. So now I'm going to go to my calculator, and I'm going to do a two-sample or two-prop z test. So here's two-prop z, because I have two proportions that I'm comparing to each other. So one from Illinois, one from Michigan. X1, N1 is my Michigan stuff, because that's my first number here. So 950 and 1020. So number of successes, number of samples. Same for Illinois. 910 pets. 910 had a pet out of 980 that were asked. And I'm testing whether Michigan, which is P1, is bigger than Illinois, which is P2. That's this one right here. I can put a little claim by it because that's my claim. Calculate. So my z-score is 0.245. So my z-score, my test stat is 0.245. My p-value, come on, is 0.40. So my p-value is 0.40, which is, 0.40, which is definitely bigger than 0.05, right? 40% is definitely bigger than 5%. So we're going to fail to reject HO. So we failed to reject HO, which means that my claim is not supported. So it does not support my claim. Okay, let me get a drink here real quick. Hold on. All right, sorry about that. Hopefully my mic is still working. Okay, it'd really be disastrous if I have to redo this video just because my mic stopped working. So that's that one there. Okay, two samples, two percentages that you're comparing to each other. Therefore, it's a two-prop z test, right? All right, so here we have regular M&Ms being compared to peanut M&Ms. So again, this is another two-sample test, and we're comparing their averages, right? So we're testing the claim that the average number of candies in a regular M&M's bag is more than the average number of candies in an M&M's bag that's peanut. So my claims are about two averages. Again, I'll put regular M&Ms as my first average. So mu r for regular is equal to mu p for peanut, and mu r for regular is more than mu p for peanut, and this is my claim. So because this is an average test, we're going to go to stat, we're going to go to test, and we're going to go to a two-samp t-test. Not two-samp z, two-samp t-test, because we have the sample deviations for both, right? So x1 is my regular, x2 is my peanut, just because that's how I set it up here. So in a regular bag of M&Ms, we have an average of 102 and a deviation of 3.85 out of 60 bags of peanuts, so 60. And then for peanut M&Ms, whoops, sorry, my bad. 40 regular M&M bags, my bad. So 40 regular bags of M&Ms. This is what I get for doing this late at night. For peanut M&Ms, we have an average of 98 candies. We have a deviation of 2.65, and we tested 60 bags of peanut M&Ms. All right, and we want the average of the regular M&Ms, which is mu1, to be bigger than the average of the peanut M&Ms, which is mu2. We don't want to be pooled. Never want to be pooled. So my test stat is going to be 6.04. So test stat is 6.04, which is different than what I have on the study guide for some reason. If I scroll down here, I hope I didn't mess this all up. Here I have my test stat to be slightly less than what that is. So this is what I was talking about here, that I accidentally got my deviation wrong on this one, so that this is incorrect. Although this one seems to be off a little. Let me just double check my numbers here because I was entering that in a little bit shakily there. So two-samp t-test, 102 average. Oh, that's why. Always check your work, folks. 8.5. There we go. 40, 98, 65, 60. Okay. Calculate. There we go. That's much better. So always check your work, ladies and gents, even if you're a math teacher. So my t-score, now if you did that on a final, I'd probably mark you off just by half a point if I could see it. The problem is that most of this is done in the calculator, so it's hard for me to see what you type in. That's why it's always good to write your stuff on paper, folks. So 5.728. My p-value is 1.5 times 10 to the negative 7th. 0.5 times 10 to the negative 7th, which we've already established is much less than 0.05. So we're going to reject HO because it is a rare event, and therefore we're going to support my claim because my claim was not rejected along with HO. My claim was outside of HO, so good for me. All right, so that's that one. And now we get into some of the more tricky ones. So we're testing to see whether a standard knife and a quick slice knife have difference in slice time. So the claim here is that we can slice up stuff quicker with this quick slice knife than got the hiccups there, sorry, than we can with the standard knife. Excuse me. And again, hiccups at the wrong time here. So they're slicing up some monkey brains, and these were the times that took them. So this guy sliced up monkey brains 30 seconds with a standard knife, 25 seconds with a quick slice knife. This guy cut the monkey brains up 45 seconds with a standard knife, 43 seconds with a quick slice knife, and so on and so forth. So is there enough evidence to test that there is a difference in slice time? So the key word here being difference. It is an average, and we do have two samples, but they're what we call matched pairs because this is one person's for both, this is one person's time for both, this is one person's time for both. So because it's a matched pairs situation, we're going to be testing the average difference. So it's going to look like this: HO, H1, mu D, average difference, mu D, average difference, equal to 0, which means there's no difference, not equal to 0, which means that there is a difference. And so we're claiming that there is a difference. So we're claiming this right here. We're claiming that there is a difference, that the difference between standard and quick slice is not 0. So what do we do here? This one's a little trickier. First off, we enter these numbers into our two lists. So 30, 45, 42, 38, 49, 32, 20, 39. We don't need the 29 there. So on the other side, we have 25, 43. I know this is riveting, folks, so if you want to skip ahead, I won't blame you, but you might miss my clever quips and jokes along the way. Yep. Although I'm almost done anyway. 30, 19, 37. All right. So now we're going to go to L3 here, and we're going to say, hey, L3, you're going to be L1 minus L2. Because then we're testing the difference, right? So it might as well make sense to actually make the list different. We want to get the difference between lists. Boom. Here's our list of differences. Now you can see right away that it looks like each time it's pretty different than 0. We have one where it's exactly 0, but they look fairly close to 0. But we have these here where it was a lot different, more different than the standard knife, right? So here was pretty large differences. Here were not so much difference. So is there enough evidence to say that the difference is usually 0? Well, that's what we're going to test. So we're going to go to stat, test, not to sample. This is where the trick comes in. We're going to go to a simple t-test because we're going to test a list. In this case, we're going to go to data, and we're going to test 0 first off. That's our initial, and we're going to test the data in L3. We're going to test one sample contained of all the differences. So we basically took two samples, combined them into a list, and we're going to test that. Make sure we put a not equals to there, calculate, boom, there's our data. So my test stat is 2.22. Let me just make sure I got this right on the study guide here. Yes, so my test stat is 2.22. My p-value is 0.061. And 0.061 is definitely less than definitely more than rather. It's more than 0.05. So because the p-value is bigger than 0.05, that means we're going to fail to reject HO. So we're going to fail to reject HO, which means that there is not enough evidence to support the claim. So it does not support the claim, right? There's not enough evidence to say that the quick slice. So basically, if we look at our list here, even though that there was a difference for a large majority of them, where's my list? So even though for each person there was a difference in slice time, it wasn't big enough to say that the difference was 0 on average, right? Because yes, this guy right here went a lot faster. This guy went faster, but not by much. This guy had a faster time, but again, not by much. And this guy had the exact same time. This guy had a slower time, and these last three were also again faster, but not by much. So they weren't fast enough to say that the quick slice knife actually made a difference in slice time, right? That's what this is saying here. Now, the confidence interval stuff is actually pretty easy. Once you do that, once you got your list done, you can simply go to stat, tests, and you want a t interval. And you just do the same thing you did last time, except that you're doing an L3 and you're doing a t interval. And so you just go to calculate, boom, give it time, give it time. There you go. And then we get our numbers here, negative 0.102 and 3.35. So negative 0.102 and 3.35, and mu d is somewhere in the middle here, so that's mu d. And like I said, this backs up my claim. This backs up my stuff here, because 0 is inside this interval. So it makes sense. You have if we're doing a 95% confidence, which is what we are, it makes sense that that we did not support, because 0 is a possible difference, right? It is a possible answer to the situation, and therefore you don't have enough evidence to say that you rule out the possibility that there is no difference. Because you cannot rule out the possibility that there is no difference, you have to assume that there is no difference. Okay. So yeah, these two, by the way, these two do not always agree. There are some rare cases where your interval will give you one notion, and your um, uh, hypothesis testing will give you a different notion. So sometimes these can disagree. Sometimes this will imply not support. Sometimes this will imply support. Remember, this is a fail to reject if 0 is inside the interval. If 0 is outside the interval, then it's a rejection. So usually these agree. If you're failed to reject here, then you're 0 inside this interval. But that doesn't always happen, just usually. So don't freak out if on this final whatever, this is not 0. Or don't freak out on the final if these two do not agree in their conclusions, because sometimes it does happen. Double check your numbers for sure, but if you double check them, triple check them, and you're sure you got the right numbers here, then don't freak out. Trust your gut. All right. So zookeepers measuring food. Out of their 20 herbivores, the cost per animal was that with a deviation of that. Carnivores with that. Test the claim. So we're testing the claim about a variance here, right? We're testing the claim that carnivore cost varies more than herbivore cost. So we're claiming a deviation. So we have sigma, 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 sigma. Now remember, with sigma, the highest deviation has to be your first number. So in this case here, um, let's see here, herbivores have a deviation of 0.95. Carnivores have a deviation of 1.35. So because carnivores have the higher deviation, they have to be the first ones in my setup here. And then herbivores would be the second one. So equal to and then bigger than, right? So remember, when you're testing a two sample variance, because this is what this is, right? We have two samples, herbivores and carnivores, and we're testing their variance, then the bigger variance has to be the first sigma. Okay? And this is my claim, that the carnivores varies more than the herbivores. Now, this one we actually can do in our calculator, thankfully enough. We go to test. This one is an F test. Where is it? I just passed it, didn't I? Oh, there it is. Two sample F test. So this is an F test. And we go to stat. And this one's pretty simple. You just type in the number again. So standard deviation for the first, which remember is the bigger of the two. So 1.35, right? I want the carnivores to be first because they have the bigger deviation. And outside of that, I tested 18 carnivore meals. Herbivores were 0.95, and I had 20 of those meals. And so my claim is that the carnivores is more than the herbivores. All right, and we get my test stat of my test stat of 2.01 or 02. So my F is 2.02. That's my F, which, yeah, okay, that agrees. I was making sure I got it right on the study guide, which I did. And then my p-value is 0.07. So 0.07 is my p-value. And 0.07, once again, is bigger than 0.05. So we're going to, once again, fail to reject HO, which is going to not support my claim, right? Because if we fail to reject, that means we're going to go with that. C is outside my box. I don't support it. Okay? All right, so last one here. Almost the end, folks. This one is not a test. This one is one of the things that we did more recent, which is regression. So find the best mathematical model and then write the regression equation, correlation coefficient, coefficient determination, all that good stuff there. So first thing we're going to do, enter my data, right? It's a common theme in stats if you haven't gotten that throughout the years. So 30, 25. I'm sure you guys don't want me to read off these numbers all the time, so I will make the best attempt for me not to read them off as I'm typing them in to spare you the pain of your ears bleeding either mentally or physically. I know I can have that effect on you guys sometimes. So it's a special gift of mine, you can say. And this is the punchometer score. So ideally, you think that the more time you spend chopping trees, the stronger your arms are, and therefore the higher score you would get on the punchometer. Now, we're going to see if that is indeed true, right? That would be the logical conclusion, right? The more time you spend chopping trees, the stronger your arms are, the higher score on the punchometer. But we'll see if that actually holds water here. All right, so we got all this data in here. Stat, calc, linreg test. Now, actually, sorry, my bad. It says find the best mathematical model, right? So if it says here find the best model, that means it won't necessarily be linear. It could be, but it won't necessarily be. So we're going to test all of them here. So let's go to linear first. It has an R of 0.996. So linear has an R of 0.996. Remember, our goal is to choose the one with the best R here. So let's go to quadratic. Actually, you know what? Let's just do second stat plot. I'm going to turn my stat plot on. And then we're going to look at this in a stat plot. Make sure I don't have that clear. Yeah. We're going to look at this in a stat plot, so zoom stat, and see if we can't estimate it from there. Well, actually, that looks pretty darn linear to me, actually. So it's probably going to be linear, but let's just check the other ones just to make sure. So quadratic. So quadratic has an R of 0.992. That's an R squared, though. So let's go ahead and square root 0.992 to get its R value. 0.9959. So it's actually pretty close to linear, to be honest. So quad is 0.995. So that's pretty darn close. Actually, if you round up, it'd be 0.996. That should be tied with linear quad, because if we round up, it'd be 0.996. What was linear again? Linear actually might be less. 60. So linear actually is still a little bit more because it was 0.996, where I had to round quad to be 0.996. So they're pretty darn close, but linear still wins out so far. Let's test the other ones just to be sure. Again, I'm checking their R values, and right now 0.996 is bigger than 0.995 because, again, I had to round this to get to the same. lnreg was the other one, 0.994, so that one's not going to work either, although, like I said, that one wasn't too bad either. And then exponential was the last one, 0.994. So once again, not too bad, but also not too great. Not better than linear. So linear is the clear winner here. Or not the clear one, but linear is the close winner here. 0.996 was better than all those. So since we decide on linear, we're going to write that equation. So it's going to be 0.1111x plus 3.089. So 0.1111x plus 3.089, right? That was 4 ones, correct? 1, 2, 3, 4. Yeah. So that's my equation. What's the best predicted score for the punchometer for someone who spends 1 hour chopping trees? Well, 1 hour is 60 minutes, and this is in minutes. So we're going to do 0.1111 times 60 plus 3.089. We just plug 60 in for x, and we get our answer, which in this case is 9.755. And then this one, again, what's the best predicted time someone would need to spend chopping trees to earn a score of 9? This one's the same thing, but in reverse. Remember, this is equal to y. And so I want to know, what does x have to be to get y to equal 9 in this case, because I want a score of 9. So I just set up as an algebra equation, 60 plus 3.089. Whoops, not 60, my bad. That should be an x in there, because I don't know that x is 60 here. X. And then you solve this equation. So you subtract 3.089, subtract 3.089. 9 minus 3.089. We get 5.911 equals 0.1111x. And then we divide by 0.1111 divided by 0.1111. And we get 53.2 is equal to x. So you have to spend 53.2 minutes, according to this prediction, chopping trees in order to get a score of 9. Now remember on this one right here, that this was one we did, I didn't put this on the study guide, but this is something we did in the very last test. If I ask you to make a linear regression, and then I ask you to predict what the best outcome is, you should always test what your R is compared to your critical value to make sure your equation works. So for instance, this R was 0.996. Well, how do I know that R is good enough? Maybe that's not. Maybe I'm better off just using the average. Because remember, that's the other way we predict. If I ask you to make a prediction, you can simply take the average of these numbers and use that as your prediction, right? But how do you know whether to just use the average or whether to use your equation? Well, you test it against this table right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 pairs of data, right? So we have 9 pairs of data. 0.05 significance means my critical value is 0.666, right? 0.666. So that means that my R value is more than my critical value. So therefore, I can use my equation. My equation is a good predictor because my R value was more than my critical value. If my R value, say, had been 0.2, well, 0.2 is less than 0.666. So if that's the case, then if I asked you what's the best predicted score, you'd simply take the average score of these and use that as your answer. If I said what's the best predicted time someone would need to spend chopping trees, you simply take the average number of trees and that's your best predicted answer. So you use the average of scores if your R value is too low, if it's below the critical value. If it's above the critical value, then you can use your equation as your prediction like we did here, and you're golden. Okay? So I'll just go through the top part as well, just for funsies here, because I'm feeling like that, I guess. What kind of test would you use if you're testing a single sample for a proportion of percent? Well, that is a z-test. Z-test, proportion percent is always z-test. There's nothing else. Always z-test. If you know the population deviation and you're testing an average, you also use a z-test. Remember, on the calculator, this is one prop z. So if you're doing this on the calculator, this would be called one prop z, and this would be called the z-test. So make sure you don't get those too confused in the calculator. But in general, it's still a z-test. If you're testing for a average with an unknown population deviation, then you're doing a t-test. Right? A t-test is for unknown population deviation. And if it's a single sample test for a standard deviation or variance, then you use a chi-squared test. Remember, this is the only test you have to do by hand. The other tests you can do on the calculator. This is the only one you have to do by hand. And then fill in blank. So a normal curve has a bell shape to it. So remember, a bell shape is like this, right? So bell-shaped graphs are normal curves. Values that are used as cutoffs when comparing tests. So if you're comparing test stats, not p-values, but if you're comparing test stats, you're comparing them to the critical values. Right? Test stats are compared to critical values. If you're testing for significance, then usually, if you're not using a critical value, usually you're using a p-value, right? Those are our two comparisons. Test stats compared to critical values, or alphas compared to p-values. Stronger correlations are closer to 1 or -1. The accuracy of a regression equation is affected by the size and scope of the data. So the more data you have, aka the size, the better. And the farther that your data reaches, so the more spread out your data is, bigger scope is better. A negative correlation is when one variable goes up as the other goes down, or vice versa. As one goes down, the other goes up. A positive correlation is when one variable goes up as the other goes up, or goes down as the other goes down. So again, positive correlation means they both agree in the direction. Negative correlation means they both disagree in the direction. Again, these will be the questions that will be multiple choice on your quiz. So I might say, what kind of test do you use when you're testing a proportion? And they'll have z-test, t-test, chi-squared, or f-test, or something like that. So these will be in multiple choice form on your quiz or on your final. So just be aware of that. These will be pretty much as is, right? I'll give you a situation, ask you to do a hypothesis test. So you need to make sure you be able to pick what kind of test you do, one sample, two samples, Z, T, chi, or F, and then make sure you can get me the data points. So your hypotheses, point, test score, point, p-value, point, failed to reject, point, not support, point. Make sure you have all the components of your answer, okay? So that's it for this video. Hopefully it wasn't too long. And like I said, good luck on the final. It shouldn't be that hard if you study this over. And again, I'll be available if you have any questions via email or anything like that, right? Or before and after school. Although right now, as I'm making this, your final is on Monday and this is a Friday. So, but if you're looking at this next year, maybe not. So I'll see you later.